I am Rajesh Khanna, Assistant Professor of Physics, Nehru Institute of Technology, Coimbatore. In the lecture 3, we are going to discussing about how to determine the Young's modulus of the material of the beam by the method of uniform bending. The lecture 3 contains 2 sessions. Session 1 comprised of uniform bending. What is the experimental setup by the animation method and the definition of moment of a force. So, the session 1 contains what is meant by uniform bending, simple experimental setup, and what is meant by moment of a force. And the session 2 contains to determination of Young's modulus of the beam by the method, theory as well as experimental setup. Enter into the session 1. First definition, what is meant by uniform bending? This is the simple diagram for explaining what is meant by bending with the uniform type. Every element of the beam is bent with the arc of the same radius of curvature and the beam is loaded uniformly on both the ends. That means this is the simple beam. We have to apply the load on both the ends. Here there are 2 ends, one end is an A and another one is an B. We have to apply the load at both the ends, uniform loaded. Due to the uniform loading, the beam also bent with the uniform radius of curvature. This type of bending is known as uniform bending. That means we have to apply the load at both the ends uniformly so that the beam also bent with the same radius of curvature. That is known as uniform bending. This is the simple experimental setup for explaining the uniform bending. This is our beam, plastic, made up of plastic. At the 2 ends, the 2 weight anchors are there, and also we have to apply a uniform load to the weight anchor. So, the beam will bend uniformly. This is the simple experimental setup for uniform bending. Next one is what is meant by moment of a force. You know, in the previous class also, moment is nothing but some rotational effects. The moment of a force with respect to the point is defined as a simple turning effect or rotating effect of the force produces with respect to the point. That means with a fixed point, we have to apply a force. The body will rotate. It will produce a moment of a force. What is the measuring quantity? How it is measured? It is measured as the product of one of the force and the perpendicular distance of the force from the center of rotation. Just listen this diagram. This is one object or one beam with a fixed point. This one is a fixed point. With the fixed point, the body may rotate with application of the force F. So, we have to calculate the moment of a force. This is the simple product, force into perpendicular distance. Here, we are going to calculate the moment of a force. The 2 terms are there. One is in force, another one is in perpendicular distance. The force is here. This is the perpendicular distance of the force. By the product of force and the perpendicular distance, we get a moment of a force. Therefore, moment of a force equal to force into perpendicular distance. That is equal to F into D. The unit of moment of a force is Newton per meter square. Newton is for force and distance per meter square. This is the simple definition of moment of a force. Now, we enter into session 2. Welcome to session 2. This session contains to determine the Young's modulus of the material of the beam by theory as well as experimental methods. On the basis of OBLF, in the lecture 3, our course objective is to understand the Young's modulus of the beam using uniform bending methods. That means our course objective to understand the Young's modulus of the beam by the method of uniform bending, and the general objective to study the elevation of the beam by the method of uniform bending and also determine the Young's modulus. We have to determine the elevation by the method of uniform bending and also determine the Young's modulus of the beam. The specific objective of the topic, what is meant by Young's modulus, what is meant by uniform bending method, how to determine the internal bending moment of the beam, and also determine the Young's modulus of the rectangular and the circular beam of cross section of the beam. This is simple knowledge dimension cognitive process. The weightage is here. This is the simple sketch of uniform bending methods. This is our beam. In the beam at the two ends C and D, we have to apply the equal load applied so that the beam will be bent. Through the microscope we are taking the readings how the beam becomes elevated. In the later section we are going to show and some of the animated video for this one. These are some of the equations we are going to discuss, we are going to derive in this section. External bending moment is equal to internal bending moment, that is WA is equal to YIG by R. From this we have to calculate, we are going to calculate the elevation of the beam. X is equal to WAL square divided by 8YIG. Simulative questions. Some of the simulative questions we are going to discuss. Define uniform bending. It is the uniform bending is nothing but every element of the beam is bent with the same radius of curvature and the beam is loaded uniformly at both ends. The bent beam forms an arc of the circle. Define bending moment of the beam. The bending moment is the reaction induced in a structural element when an external force or moment is applied to the element causing element to bend. These are all some of the simulative questions. This is the students activity mind map. After complete of this session, you have to try to draw a mind map. This is the simple flow diagram for explaining the concept of uniform bending. Elasticity general one, Hooke's law. Based on this Hooke's law, based on the Hooke's law, there are three types of modulus: Young's modulus, bulk modulus, and the rigidity modulus. This is our main topic to determine the Young's modulus by the method of uniform bending, that is an elevation of the beam, theory as well as experimental concept. This is the session objective. After end of this class and session, the students are able to understand concept of Young's modulus by the method of uniform bending. This is the simple setup. This is an important question also. Young's modulus uniform bending method. From this we have to determine the elevation at the center of the beam by the method of applying load at both the ends. This is the simple diagram. Let us consider a beam of negligible mass supported symmetrically on two knife edges. This is our beam CD. At the end of the two ends of the beam, we have to apply a load W with the help of two supported knife edges. Here, that A and B represent the two knife edges. Let the length between A and B is L. The length of the beam is L. This is the length of the beam from the distance between the two knife edges, L. Let equal weights W be added to either end of the beam C and D. This is the two ends of the beam C and D. At C and D we have to apply the uniform loading W. Let CA is equal to BD. Listen here in this diagram. Let CA is equal to BD. CA is here, BD is here. CA and BD are at equal distance. That means we have to apply the equal load at the equal distance from the knife edges. So it is called uniform bending. So it is CA is equal to BD. Due to the load applied, the beam bends from position F to E. This is the before applying the load. This is the position of the beam. Due to the application of the load, the beam moved to F to E. That is, due to the application of the load, the beam bends from F to E into an arc, a circle. It will produce a elevation X. When before applying the load, the beam is normally at the F position. Due to the application of the load, the beam moved to F to E. Therefore, the elevation X will be produced. Let W be the reaction produced at the point A and B acts vertically upwards as shown in the figure. Just listen. This is the action W. This is the reaction. This is the action load W. Due to the application of the load, the reaction will be produced. This is the W. This is mentioned here. Consider a point P on the cross section of the beam. Consider a point. This you have to consider small portions B here. Here you have to consider small portions P on the cross section of the beam. Then the force acting on the part PC. Here P. This is the C. This is the portion P. This is the C. Therefore, the forces acting on the part PC of the beam, that is one is an action, another one is a reaction. The force W at the C is an action. The force at the A is known as reactions. So this is reaction, this is action. This is action W, this is reaction W. So this one is an action, this one is a reaction. So based on this, we have to apply a simple moment of a force. This is the simple beam. Here there are two forces are there. Due to the load applied, what is the action, what is the reactions? let the distance PC is equal to A1. Listen here, P is here, C is here, the distance between is A1 and PA is equal to A2. P is here, A is here, distance between these two is A2. Then the external bending moment is equal to P is equal to MP is equal to W into A1 minus A2, that is a force into perpendicular distance. This is the force into perpendicular distance. Therefore, MP is equal to W into A1 minus A2, or MP is equal to multiply W into A1 minus W into A2. Here, the clockwise moment is taken as negative and the anti-clockwise moment is positive. That means this is an clockwise, A2 is negative, and that is an anti-clockwise, A1 is positive. So, here taken as clockwise is taken as negative and the anti-clockwise taken as positive. Therefore, from the external bending moment about P can be written as from this equation, that is MP is equal to W into A1 minus W into A2. MP is equal to W into A1 minus A2. This is nothing but A. A1 minus A2 is nothing but A. Therefore, MP is equal to W into A. This is equation number 1. We know the internal bending moment is equal to YIG by R. Under equilibrium condition, the external bending moment is equal to internal bending moment. Under equilibrium condition, the external bending moment is equal to internal bending moment. Therefore, equation 1 is equal to 2. Therefore, W is equal to YIG by R. This is equation number 3. Equation 1 is equal to external bending moment. Equation 2 represents the internal bending moment. Under equations under equilibrium, the equation 1 is equal to 2. Therefore, W is equal to YIG by R. That is equation number 3. From the diagram, for a given load W, Y, I, G, R, these are all constants. This is an Young's modulus, moment of inertia, the radius of curvature are constant. Here it is found that the elevation x, this is elevation x of an arc of the circle of radius shown in the figure. This is the beam. Due to the application of the load, the beam is elevated to a distance x to E. That means, here listen here, this is the same diagram. From the triangle AFO, here AFO, from the triangle AFO, this is a right angle triangle, OA square is equal to AF square plus FO square. Listen here, OA square is equal to AF square plus FO square. This is a simple hypotenuse square is equal to side square plus side square, that is OA square is equal to AF square plus FO square. Here OF is equal to FE. OF is equal to FE. OF is equal to FE. Here FE is nothing but x. Therefore, OA square is equal to AF square plus FE square. Instead of FO, we put an FE. Therefore, AF square is equal to OA square minus FE square. Rearranging the equations, AF square is equal to taking the FE on constant outside. FE is equal to OA square by FE minus FE. This is equation number 4. Here, AF is equal to L by 2. Here, AF is equal to L by 2 and FE is equal to x. Once again, AF is equal to L by 2 and FE is equal to x, that is equal to R by 2. This is R by 2, this is another R by 2, and OA is equal to R. OA is equal to R. Therefore, substituting these values in equation 4, therefore L by 2 square is equal to x into R square by R by 2 minus x. On simplification, L squaring, L square by 4 is equal to x into 2R minus x, or L square by 4 is equal to 2xR minus x square. If the elevation is very small, then the term x square can be neglected. Because x is small, we have to take the x square, the value is still less, so we have to neglect the x square. Therefore, we can write L square by 4 is equal to 2xR, or x is equal to L square by R. From this, we have to calculate the radius of curvature R is equal to L square by 8x. This is equation number 5. The radius of curvature R is equal to L square by 8x. That is equation number 5. Therefore, substituting the value of R in equation 3. Here 3 is here. Here the R value is here. Substituting the value of R from this equation 5. Get that done. We get the value WA is equal to YIG by L square divided by 8x, or WA is equal to, on simplification, 8YIG into x divided by L square. This is equation number 6. Rearranging the above equation, get the value of elevation of the beam, that is an x. From the rearranging the above equation, we have determined the elevation of the beam. X is equal to WAL square by 8YIG. This is our required answer. This is the elevation of the beam. That is, once again, the elevation of the beam Above A is x is equal to W AL square divided by 8y Vj. W is the load applied, A is the breadth of the beam, length of the beam. This is the Young's modulus. This one is the moment of inertia of the beam. Now we are going to see an animated video how the experimental setups are there.
The beam for which the Young's modulus has to be found is placed on the two knife edges as shown at equal distances. Two weight anchors, that is dead loads, are suspended, one each at either side of the beam at equal distances from the knife edge, and the pin is focused through the microscope. The tip of the pin is made to coincide with a horizontal cross wire as shown, and the reading is noted. Now, the weights are added on both sides simultaneously in steps of 50 grams. Each time, the tip of the pin is made to touch the horizontal cross wire, and the readings are noted from the vertical scale of the travelling microscope. The same procedure is followed until the maximum load is reached. The similar procedure is repeated again by unloading the weights in steps of same 50 grams, and the readings are tabulated. Using the observed data, the elevation is calculated.
These are all some of the objective type questions based on the lecture. First one, a beam is said to be of uniform strength if the conditions bending moment is the same throughout the beam. Second one, shear stress is the same through the beam, deflection is the same throughout the beam, and the fourth one is the answer, the bending stress is the same at every section along its longitudinal axis. What is the reason? Second one, the stress in a beam due to a simple bending is directly proportional or inversely proportional or curvilinearly related or none of the mentioned. Okay, the answer is the directly proportional. What is the reason? Which stress comes when there is an eccentric load applied? The answer is an bending stress. What is the reason behind that? You have to apply it as an assignment. And the fourth one is on bending of a beam, which is the layer which is neither elongated nor shortened. The neutral axis is the answer. And the fifth one is the bending stress is directly proportional to distance of layer from the neutral layer. What is the reason for that? All of you submit the reason as an assignment. Thank you.